Modern Aircraft Cockpit Systems. Welcome to this presentation on modern aircraft cockpit systems. From the Wright brothers' completely exposed controls to today's sophisticated glass cockpits, aircraft cockpit design has undergone a remarkable transformation. Modern cockpits represent the pinnacle of human-machine interface design. They integrate advanced electronics, carefully designed ergonomic principles, and multiple safety systems to enable safe and efficient flight operations across both civil and military aviation. The evolution of civil aircraft cockpits. Civil aircraft cockpits have evolved dramatically from simple mechanical controls to sophisticated glass cockpit systems featuring electronic displays. This progression reflects decades of technological advancement and human factors engineering. Modern glass cockpits utilize digital technology to provide comprehensive displays of critical flight data, replacing traditional analog gauges and dials with intuitive, integrated information systems. What's important to note is the crew-centered philosophy behind this evolution. The transformation ensures that automation enhances rather than replaces human decision-making, while maintaining ultimate pilot authority over aircraft control. Glass Cockpit Technology Overview. Let's look at the key components of glass cockpit technology. The primary flight display, or PFD, shows attitude, heading, airspeed, altitude, vertical speed, flight path guidance, navigation data, and engine parameters with integrated warnings. The Multifunction Display, or MFD, presents navigation charts, moving maps, weather radar, meteorological information, cast data for traffic awareness, and system status monitoring. Finally, the electronic flight instruments provide integrated digital flight instruments with real-time data processing, backup redundancy systems, and interfaces with flight management. Computers. Together, these components give pilots consolidated access to all critical flight information. Military aircraft cockpits, unique challenges. Military aircraft cockpits represent specialized human-machine interface design, optimized for combat operations, mission effectiveness, and pilot survivability. Unlike civil aviation, military cockpits must address extreme physical stresses and unique operational demands. First, high-G environments. These systems must withstand sustained forces up to 9G with extreme acceleration, deceleration, vibration, and shock loads. Second, temperature extremes. Rapid temperature changes and environmental conditions never encountered in civil aviation operations. Third, electromagnetic warfare systems must function reliably in hostile electronic environments while supporting rapid decision-making under extreme stress. These challenges make military cockpit design one of the most demanding engineering problems in aviation. Multi-function displays, the cornerstone of modern avionics. Multi-function displays integrate multiple aircraft systems into unified, programmable interfaces. Instead of numerous analog gauges scattered around the cockpit, pilots access flight data, navigation maps, engine parameters, and weather information in one reconfigurable screen. MFDs significantly decrease cockpit clutter and enhance situational awareness by consolidating information presentation. Commercial aircraft like the Airbus A320 and Boeing 737 use MFDs to display navigation and system status, while military jets provide tactical data, targeting information, and sensor imagery. Pilots can switch between displays depending on flight phase, showing navigation maps during cruise or approach charts during landing. This flexibility makes MFDs essential to modern aviation. MFD technical architecture and construction. Now let's examine the technical architecture of MFDs. The hardware components include high-resolution LCD or AMLCD color screens, typically 8 to 15 inches, microprocessor or FPGA for processing, touch screen interfaces or cursor control systems, memory modules for data storage, and dedicated control panels with push buttons. The core electronics consist of power regulation circuits, data processing units and interface modules, and communication interfaces such as ARINC 429 for civil aircraft and MIL, STD-1553B for military aircraft. The display itself consists of liquid crystal material layers sandwiched between polarized filters with backlighting for illumination. MFDs receive data from aircraft subsystems, process information in real time, and render composite graphical output. Pilots interact via control panels, bezel buttons, or touch screens to reconfigure display modes based on their needs. Multifunction keyboards, programmable control interfaces. Multi-function keyboards provide pilots with programmable interfaces for aircraft system interaction and mission parameter configuration. The MFK acts as the primary control interface, replacing multiple dedicated switches and knobs. Through the MFK, pilots enter waypoints, flight plans, communication frequencies, and system commands displayed on the MFD or linked with the flight management system. These keyboards are backlit for night operations and include shortcut keys for quickly switching display pages or activating avionics functions. In commercial aviation, the MCDU serves a similar role, while military aircraft MFK panels control mission-critical systems such as radar modes, targeting pods, or electronic warfare equipment. The main benefit is centralized control, reduced pilot workload, and faster access to complex avionics functions. MFK operational modes and construction. MFKs operate in three primary modes. First, page display mode. The MFK receives page information from the mission computer in binary format, validates data, and converts it into pilot-readable values. Second, page request mode. Software processes pilot page requests and sends messages to the mission computer to retrieve details for new displays. Third, identification mode. During initialization, the MFK sends hardware and software version information to the mission computer for system configuration verification. Regarding construction, MFKs feature a robust chassis with programmable push buttons, backlit LCD or OLED displays, and embedded processors. Internal components include microcontrollers, logic boards with EEPROM or ROM, interface transceivers such as RS-422 or MIL, STD-1553B, and rugged key switches for tactile feedback. EMI shielding ensures cockpit safety and reliable operation in the electromagnetic, rich cockpit environment. Head-up display, eyes-out flying technology. Head-up display technology represents one of the most significant advances in aircraft human-machine interface design. HUDs project essential flight information directly into the pilot's forward line of sight via a transparent combiner glass, enabling what we call head-up, eyes-out flying. Pilots maintain visual focus on the outside environment while simultaneously monitoring speed, altitude, heading, flight path, and approach guidance. HUDs are particularly valuable during low-visibility conditions and instrument landings. Civil aircraft display flight path vectors and ILS approach cues, while fighter jets show weapon aiming symbology and target designations. This technology improves safety and efficiency by minimizing head-down time and allowing continuous visual reference outside the cockpit, which is critical during approaches and combat operations. HUD technical architecture and operation. Let's examine the technical components of HUD systems. The system includes a projector using LEDs or lasers, an optical collimator for image arrangement, a partially transparent combiner glass, and a dedicated HUD computer for symbol generation. Here's how it works. Flight data is processed by the HUD computer and projected onto the combiner glass. Collimation ensures displayed imagery aligns with real-world visual cues at infinity focus, allowing pilots to maintain eyes outside while referencing instrument data. The collimator arranges light from the projector so it appears to come from a distance, eliminating the need for pilots to refocus their eyes between the display and the external environment. Advanced HUDs display flight path markers, targeting symbology, and approach guidance to reduce head-down time and improve safety in low visibility or complex operational conditions. This seamless integration of digital information with the real world is what makes HUD such a powerful tool in modern aviation.